how we added some features to OpenStack Nova to enable high-performance VMs. This is a bit awkward. Yes, it's a little bit heavy. Okay, so a little bit about myself. I'm a software engineer at Red Hat. I've been working on OpenStack Nova since 2012, and I've been a core developer on the Nova project that I'm going to talk about a little bit more soon, since 2013. Yeah, so a little bit about this talk. I will speak about OpenStack and the elastic cloud and what that means, how we designed it. I will talk about why high performance requirements are interesting for certain users. Then I will talk about a set of features that we actually added to OpenStack that enable or that help enable high performance workloads in the cloud, namely NUMA support, huge pages support for CPU pinning, and for I/O device locality. And then I will talk about some of the challenges we faced with designing and fitting this into the OpenStack, and why this was not as straightforward as just using the features that exist in the lower virt layers. Okay, so a little bit about OpenStack. It's a set of open source projects that are supposed to help users build out cloud infrastructure. It's, as we said, it's open source. It's mostly written in Python. It's a number of projects that help users provide access to compute, networking resources, block storage, and some other stuff that can be useful through a API, to an HTTP API. So it's star as a service kind of thing. It's a set of tightly integrated, or in theory tightly integrated, open source projects that have common governance and technical committee that oversees a direction. So for people who are not familiar with how it works, those are different projects, but there's a body that is heavily involved in setting the direction of the technology being developed. And all of the projects expose an HTTP API that users can use, and also other services can consume as well. So a little bit about OpenStack Nova itself. So it's infrastructure as a service project in the OpenStack ecosystem. It's supposed to let you manage compute resources through a REST HTTP API. So it allows, or it schedules and provisions virtual machines across your cluster of compute hosts. Storage and networking for your VMs are not handled by OpenStack Nova. It's really, we won't be talking about this a lot in this presentation, but it might be worth mentioning so that people have a understanding. So there are other projects, as I mentioned, in the OpenStack ecosystem that help you do this. Networking is actually kind of special because Nova can do networking, but as I said, it's not necessarily very relevant to the stuff we're presenting here. And then it allows users to have basic VM lifecycle management, allows them to start VMs, stop them, resize them, snapshot them. It also has some primitives for the cloud administrators who can migrate, and live migrate VMs across the compute hosts. And it's built to be hypervisor agnostic, so it has in-tree drivers that support libvirt, KVM, Hyper-Vs, and VMware. There's some other out-of-tree drivers that people developed as well. But most of the stuff we will be talking here is implemented only in the libvirt KVM driver. So, since this is KVM forum, so that's. So, talk about a little bit more about the Elastic Cloud and how it might be different from the standard virt environments. So the idea or the end goal, the ideal is to be able to quickly scale out by adding provisioning new hardware. And it's central to its to what Nova itself exposes to users is the concept of flavors, where users cannot fine-tune their VMs, but there's a preset, let's say a recipe or a size of a VM that administrators set, and only those VMs can be requested by the users. This is very similar, or this is exactly the same as EC2 instance types, I think they're called. So you can get like a small, medium, large, and they would be predefined with, there's no room to fine-tune. This allows for simple scheduling, and the idea behind this, in theory at least, is to be able to focus on scale. So when you have a lot of compute hosts, your scheduling does not become a bottleneck. As we already mentioned, that there are additional services that VMs want to use that are handled by other components. And I think it's might be also worth pointing out that users have no visibility. There's nothing exposed in the user visible APIs of Nova that will tell them anything about the infrastructure they're running on. So this is a little bit of a architecture diagram for people to get who are not familiar to have a better idea. I think the most important bit to mention here is that there's the API bit, which is the entry point of the users. We have the Nova Compute service, which is the service that runs on each of the compute nodes and talks directly to the hypervisor through the driver interface. And then there's a number of other services that the scheduler one is also important. They all communicate through RPC over a message queue, and there's a shared database where some of the state of the system is stored. So as you can see, there are some other services that provide other stuff, but the central to running is the compute service and the control plane, which is the scheduler and the API. Okay, so a little bit about how Nova schedules VMs. Flavors, as I already mentioned, are the central bit. So they are admin controlled, so admin defines them and exposes them to users, and users can request VMs of a certain flavor. Some limited stuff can be overridden through image metadata, but it's not really relevant. Probably should have removed it from the slide. So the way it works is that each compute host exposes its resources to the central scheduler, and for each request, the scheduler runs a set of filters, which is basically a function that says yes and no based on my policy. This host fits or passes or doesn't pass, and it runs this in a loop through a list of all the hosts it knows about. The result of this is a smaller list of hosts that passed according to the set policy, and then there's an additional optional weighing step where you can order them based on some sorting criteria, like, for example, if you would like to stack VMs or spread them out. There's defaults are set in such a manner that there's overcommit, so that's in line with the idea that we want to utilize our resources as efficiently as possible, so that there's no underutilization, or at least in theory. And most of the original and basic filters do not look into the details of the host. What I mean by that is that they don't treat CPU 0 differently than CPU 25, for example. It's just about the number of CPUs. We will see why that's important later when we look into how we implemented some of the stuff that actually ended up needing to know these kind of details. And PCI devices are a little bit special, but actually they're not, because scheduler knows only about very small subset of features of all the devices that are exposed to VMs. So it's almost as if they're treated by how many of them there are, and not with their through their qualities. Okay, so a little bit about why high performance is important, why it was interesting for people, why people were asking for these features. So one example is network function virtualizations. We've heard a number of talks. I think yesterday there was a number of talks about this and how it can be done. The idea is that you want to virtualize and eventually move into your cloud, your packet processing. And the important thing here is to have predictable latency, which is not something that plays well with how all the ideas I spoke about before, about with overcommit, with very simple scheduling that focuses on just having an easy way to scale out your infrastructure. And there's also the fact that nowadays a lot of hardware has NUMA, so we want to, by having an infrastructure or the management orchestration engine like Nova aware of this, makes for better utilization of hardware, which is where we want to be, right? So, right. So the a little bit to hint at what the issues when designing these things and exposing them to the API that Nova has is that we cannot rely on users understanding or having knowledge about the hardware their workloads will be running on. So we needed a way to expose this to users by honoring the concept of flavors. And flavors were the right way to put this, but we needed to design those knobs in such a way that they make sense to an end user, and they are, yeah. So the first bit was adding NUMA awareness. Modern hardware is increasingly has non-uniform access to certain regions of memory from certain CPUs. And there are, of course, benefits of being aware of these effects so that you can have a better memory bandwidth utilization and less latency. And there are certain, of course, back to NFV, there are certain NFV workloads that can benefit from knowing about NUMA effects the hardware they're running on. So that's especially interesting coupled with the I/O device pass-through. So libvirt, as I said, we are mostly using we are only using the KVM driver for any of these features. So libvirt exposes this information in its host capabilities XML, and you can see how there's actually I probably would need to scroll down a little bit. I'm not sure if I'll okay, but so yeah, there's cell, which is what libvirt calls NUMA nodes, and then there's a number of them here, how many of them are on the host, and then there's information about certain CPU and where the CPU belongs. And Nova can parse this information and then feed it back to the scheduler. So this was how can users request this? As we said, this is done through the flavors. A simple case is where you just an admin defines a flavor that allows that asks for a certain number of NUMA nodes to be exposed to the VM. If the number is one NUMA node, this NUMA will be taken into account when scheduling, because normally OpenStack would not care about NUMA, would not consider it. An instance would float across all the CPUs, which can be problematic for certain applications. So defining this to be one, which is the most common case, would make sure that the instance is confined to a single NUMA node of a host, or if it's not possible to do, it would fail to be scheduled. And then there's some other bits that can be fine-tuned. These are not, I guess, they are for very specific applications, and yeah. So some of the implementation details, I think I spoke about this already a little bit. Details of the host are exposed to the scheduler, and then the other bit of information that's important is the stuff that comes from the flavor. So we also added a specific filter that's NUMA aware that would run a placement algorithm, currently not very sophisticated, but it can be improved, that will try to fit the NUMA nodes of the instance onto the available NUMA nodes of the host. In this particular case, we can consider overcommit on a single node of the host. So once the VM once the host is decided and it's given the request to provision the VM, we then decide based on utilization on which host NUMA nodes we're going to pin our instance to, and the libvirt lets us implement this. Right, so I don't know if I was clear enough, but the idea of all of this is that users can't really request, I want to be on NUMA node 1 or NUMA node 2. This is decided by the placement logic of OpenStack Nova, and then libvirt, as we'll see, honors that. So as we can see here, this is kind of like a bit awkward example because it's asymmetric instance, but we can see that CPUs 0 and 1 are pinned to a 0, 1 CPU of the host NUMA node. So this means that those CPUs will be floated around, but only on the between CPUs of a single host NUMA node. And the same thing is for CPUs 1, 2, 3, 4, and 5. And the emulator pin is pinned to a set of CPUs that the instance is running on. So we can see here this is like continued. It would be the same instance, XML. That there's also a NUMA policy exposed to the guest operating system, and it matches the how we pinned the CPUs in the previous slide, and there's also memories allocated from memory on certain NUMA nodes. So now the next thing we did is huge pages support, and I'll let Sahit tell you more about this.
So hello, my name is Said. I'm software engineer for Red Hat, and I joined Nikola on some topics related to high-performance VMS. Today I will try to talk with you about HIGH-PERF on Nova. So the motivation, it's mostly related to performance. We will actually try to improve the access time for a virtual machine to its memory by reducing the number of TLB misses, and so that can result for some applications a huge improvement. So virtual addresses needs to be translated to physical. This consumes some CPU time. In average, we talk about 10 to 100 clock cycles. So using the TLB can increase performance by much as 15%, sorry. So yes, but the problem is entries in that cache are limited. So larger pages are less physical to less virtual to physical addresses. Translation has to be stored in that cache. So if we take an example with a virtual machine that requires 1 gig of RAM, it's kind of easy to illustrate that. Using the larger page size available on the system will consume only one entry on the TLB, while keeping the default and smallest page size will consume more than 200 and 1,000 entries in the TLB. But there's something we have to keep in mind. Using each page is guarantee, and so reserved memory for the virtual machine. So even if the virtual machine does not use all of this memory, so I mean it's not possible to use overcommitment in that case. So to request each pages will Nova, it's kind of easy. You may have to set a special property on the flavor. So the operator will have several options: large, any, or custom size. When you want to put an instance with its memory bucket with each pages, you need to use large. If you just have a preference to use each pages, you may use any. It will actually fall back to the smallest part available on host if it's not possible to handle the large request. Also, if the system provides several page size, you can set the custom one you want to use. Also, there is a special case with any. If the flavor is configured with any, it brings to the user the possibility to set a specific to use or not each pages by updating the image property. So each pages is implemented on top of NUMA. That means it takes advantage of its memory placement. So you can still control on which node on the host, on the guest node you want to assign a specific amount of memory. But currently, Nova does not support to set different page size per NUMA nodes. This is something that needs probably to be implemented in a future release. So we use at least libvirt 1.2.8 to track pages available on the compute host. and expose this information to the scheduler. So when a request comes to the scheduler, it will find one host able to handle that request by looking at the page size, by looking at the number of pages requested and the number of pages available on the host. And if one host is able to handle that request, the boot process can start. Yeah?
Can you expose the 1 gig page as well? You have just a 2 meg page with 4K and the 2 meg.
Yes, so.
How about the 1 gig page?
Oh, it's because the host is not able to handle 1 gigabyte of page size. That is what your question? I mean, this host is not able to handle.
This particular one, but yeah,
okay.
it's possible.
If
it's on host libvirt, you'll see it.
So, yeah, during the boot process, Nova will take advantage of each page's element from the memory backing to influence how virtual memory pages are backed by host pages. And as we said before, so far Nova only supports to use the same page size for all guest NUMA nodes. So thank you. Nikola, if you want to continue. Yes?
Are you relying on the huge pages already being reserved by some other?
Yes, I'll mention this a little bit, yes. I'm going to continue about CPU pinning, which is the next set of features that we added, and this is similar to huge pages. This is when we want the vCPU to have its own dedicated CPU that nothing else will run on. This can increase the performance, and this also opens up the question of treating, how do we treat hyperthreads? So I'll mention something about that as well. And this is where we notice that we are stretching a little bit what we can do with the API of Nova a little bit. So making this work in a way that you can provision these dedicated CPU VMs and then random cloud VMs that run that don't care about dedicated CPUs would mean that all of the placement filtering logic in the scheduler would have to be aware of this, and this is exactly what we don't want to do. We want to keep it as simple as possible. So what we decided to do is if you want to use this efficiently, you will need to have a dedicated set of hosts that these high-performance VMs would go to. So this is kind of related to the question you asked. You would then probably set huge pages on those hosts, and they would be kind of like high-performance. We call it host aggregates in Nova, so I'll maybe mention this later. And of course, there's no possibility of overcommit here, so this trades off the the ideal of maximizing utilization for guaranteeing performance of VMs. So this is again how we implemented requesting for it. Basically, this one is really simple. Administrator would allow Flavor to be to have the CPU policy dedicated, which would mean then that the scheduler would try to place or to pin CPUs directly to virtual CPUs directly to physical CPUs. So as I said, the way to use this is to also add a very similar flag to the Flavor that then says, and also, by the way, go to these subset of hosts, and which are only used by the instances that require dedicated CPU pinning. And there's also another knob that would tell the scheduler how to treat potential CPU siblings, but this is actually not in the main line yet. The patches are proposed, but they missed the deadline for this release, so they're a bit stalled. So yeah, implementation details are very similar to how to the team of NUMA and huge pages. So they're also built on top of NUMA. So CPU pinning automatically means that the instance would be aware of the underlying NUMA topology of the host. And as I already mentioned, in addition to that, it's recommended that the user uses a dedicated set of hosts, which is in Nova terminology called the host aggregate. There's a way to assign hosts to a certain aggregate through the API, but as you mentioned, there's also need to do special pre-provisioning of such hosts, which kind of breaks the promise that we can quickly provision new hardware and just throw it into the cloud. So that's some of the trade-offs that using this kind of features you need to live with, right? So. And we use the same features, the CPU tune element, as we did for NUMA pinning, but in this case we pin individual CPUs, and the tracking of resources is done that we mark this CPU as used, and then that would be taken into account when deciding placement. So another thing that was part of this whole set of features, this whole body of work, is PCI device locality, and this is done in such a way that libvirt also lets you expose the NUMA node the device is local to. So we then take this into account when doing. So if the instance requests a dedicated device and also requests to be pinned to a NUMA node, then we would take into consideration when doing placement whether, in addition to whether there's enough capacity on that NUMA node, whether the device is local to that. So that's more or less on this slide. Yeah, so what are the good parts of this work? The good parts is that there was a request for these features, and by adding these features, we enabled people to use our software, and then they contributed back. They fixed and reported bugs, so it's enabling people to use your stuff is, of course, a good thing. But there were some challenges related to this as well. The problem is that there's no easy way to expose these kind of details. So we had to think hard about how to make this not be completely broken but still enable people to request these dedicated resources. As we've seen, this complicates scheduling, or can complicate scheduling. The example was once you add NUMA node locality of devices into the mix, then the logic that does the placement has to know about a lot of things, and this is kind of against how the Nova scheduler was designed in the first place. And as was mentioned, there's some things you need to do to hosts before which breaks the promise of being able to quickly scale out a little bit. And then there were some challenges with the implementation of it the state of Nova. A lot of the users don't need these features. Some of the users of Nova are people who run development clouds or even public clouds, and they are not interested in these features. So they are off by default, which is never a good thing for a feature you added. And then a bunch of internals, especially in the scheduler service, needed to be refactored and brought up to bits needed to be added so that things like recalculation and pinning of NUMA would work, because, as I said previously, there was no concept of resources on a, you know, of a host. There was just a set of numbers describing the host, and now we have to talk about specific resources on the host, like NUMA nodes or CPUs or even memory pages. So that's more or less what I and Sahid had prepared. So if there are any questions about this work, well, I don't know if there's a microphone because of the, so yeah, I guess, okay.
Yeah, yes, it works, sorry. I was curious about your, whether you took performance measurements for any of these features individually or in combination. Part of the background for the question is I saw some measurements once of CPU pinning on a particular VMM, and the results weren't always positive.
So I assume we did. So to answer your question, I personally did not. I assume this is, of course, related to the actual workload you're running on. Of course, I think some of our partners did run tests. Maybe Steve, you know some.
The other thing is that particular thing I think you're referring to is usually including a little bit of oversubscription. So this kind of thing is like completely.
Yeah, in this case, I don't think it was overcommit, but it was related to overhead threads where they were running. Yeah, we found it kind of limited the ability of the host scheduler to do a good job of moving things around for that.
Yeah, when we had 2 cores per system, that was definitely the case.
Yeah, there's some ongoing work with the Red Hat performance team to benchmark a lot of this stuff. There's also, I think Dan was mentioning before the session started, the guys at CERN have been manually implementing some of this stuff because they're on a slightly older OpenStack version at the moment. But as they move to Kilo, we're hoping that they're going to be able to help out with some numbers as well. The other aspect with the huge pages in particular is for some workloads, you'll also see that larger is not necessarily better, even for some of the telco workloads. Like sometimes the difference between 2 meg huge pages and 1 gig can actually slow things down. So there's a lot of, this is one of the dangers, I guess, is that we're kind of breaking the abstraction model a little bit, and that you have to have these kind of cluster of compute nodes that are specifically tailored to that workload that you care about.
Which release these changes will be available?
This gentleman was first, so yeah, go ahead.
So my question was, to resolve CPUs, there are, I think, two options today. For example, use ISO CPUs at the boot time, right? Or use, for example, CPU set.
Okay.
Right? And you cannot, so I'm wondering, when you create a VM, what kind of command line you use for QEMU?
So what we do is we do this through libvirt, so libvirt would
Then what kind of QEMU command line that it generates?
I would have to check that.
Okay.
I don't know. Maybe some. I don't know. We use the CPU set XML element. What that translates to in
Pinning is done by libvirt.
Yeah, the pinning is done by
but
libvirt.
pinning is not sufficient because some other process of are running there, right? So.
Yeah,
right.
That's
The pre-node setup is ISO LCPUs, and then the libvirt stuff is using the CPU
right.
setup.
Yes.
If you check out on redhatstack.com, I did a blog on the pinning specifically a while back, and I'm pretty sure the libvirt XML comp is actually in that blog.
Okay.
But yeah, that's part of that you still have to preset the host.
Okay.
For this to work properly, like you said. Yeah.
So I'm a little curious about the dedicated hosts or nodes for these. Are you doing that because you don't want to track those dedicated resources in the regular nodes and accommodate for them?
So, well, the reason, I think the reason in the beginning was that at that point we would have to pollute the logic of all of the other filters. They would need to know about this. And I think it was a design decision at the time that it would be easiest, and probably what customers want would be to have a dedicated set of hosts for these kind of high performance workloads. But yeah, I think that the major problem was that the way the scheduling code works is, like I said, you have like these filter classes that just like yes or no for this host, and in case of then the normal filters for your normal VMs would need to be aware of that something's happening with the CPU pinning there.
Okay, thanks.
Which release these changes will be available?
That's a good question. So NUMA locality was available in Juno, although it had some bugs that we later fixed. CPU pinning and huge pages are available in Kilo. Right? That's with some bugs that may or may not have been fixed around where I/O threads are pinned and that kind of stuff. So you would have to look into exactly what was done.
And you said these are off by default, so do we have to rebuild it or?
No. Well, the way it works is you have to enable it in the config file. That's more. Well, you have to enable it in the config file, and you have to set your flavors to request for these things. But yeah.
Okay, thanks.
Just a quick comment. I'm wondering if maybe the term CPU pinning is not really the best thing or way to describe this, because a lot of people think of CPU pinning as like vCPU pin and picking specific CPUs. So, just referring to this as dedicated CPU resource or something like that is probably a lot more clear I would think, to the users, because anytime CPU pinning comes up, at least in my experience, they're always talking about literally pinning to specific CPUs, and obviously you do not want to do that.
No, we don't. You would get, yeah, you're right. You just get the dedicated CPU, but you don't get to choose which one.
To old virt people, they think CPU pinning and they think a specific thing, right?
Mm-hmm. It's actually like if you look at the original spec, it was framed for dedicated resourcing, but the CPU pinning references are also there to tell those people well, you're not going to get real what you expect of CPU pinning, but this is in OpenStack land what you need to look at.
Yeah.
My question is about huge pages. In the example you showed, there was just a small and a large option. How does this work with across different kinds of hardware, where you may have more than 2 page sizes, or those page sizes may be different on different CPUs?
You can respond, maybe, Sahid, but...
Well, I try to talk about that, but we have a special... You can set on the properties the specific size you want to use. So you may want to use large, any, or set a specific size.
So does this mean that the user has to know the CPU model that they're...
Not the CPU model, but yes, page is available.
That's why I'm not sure if it's... I think we implemented it and then maybe removed it, but yeah, that's where it kind of breaks. Usually you would want your users to just say users would do I want a VM that's like this high performance flavor, and then that admin then translates that by setting these specific flags into what they know about their hardware.
Yeah, so you would tell, your admin would have a different flavor for PowerPC and a different flavor for x86 anyway, right? And so then they would kind of soft document, well, this medium high performance PowerPC is 16 meg pages, so that's what you're going to get if you request one of those, right? Whereas if you choose medium high performance x86, that's going to be 2 meg.
Yeah.
Right? Something like that.
But your admin also needs to actually reserve those pages as well.
Yeah, but I think he's kind of the communication of what the abstraction means, which is very confusing.
I have another question. Maybe it's a bit silly. Don't know. I'm not a professional OpenStack user. The thing is, you said about PCI Express devices. What happens if you want to do an PCI path-through setup and you care about which NUMA node you want to run on that host to have the shorted path to the device? Is there something planned for that or something?
So that's, I think, So the scheduler would know which device of the host NUMA node the PCI device is on. Which, okay, again, which node of the host the PCI device is on, and then when doing the NUMA placement logic, if there's also PCI devices requested, the scheduler can say, okay, I have enough place to put this instance on this NUMA node, but I don't have the device, therefore this NUMA node is not considered for placement. So what you can do is assign specific devices to specific guest NUMA nodes. That's not something we can do right now. I think this was requested. This is important to some of the NFV workloads to know that you know this actual device will be on this big NUMA node where I'm running my, I don't know, DPDK, but you can't do that right now. That's something we need to fix. I don't know if that. Yeah.
Okay, thanks.
Somebody else? So FYI, that does work. Tested out Kilo with physical functions and huge pages. Everything is getting mapped with local.
Okay.
Yeah, so I have a question about the NUMA. So here you did the initial placement about the NUMA node, right? So do you plan to do the dynamic adjustment?
So no, I don't think so. That's dynamic adjustment. How? I'm not sure what you mean.
Rebalancing?
Yeah.
No. Well, yeah, I think there's actually a to-do comment in the code that says we might want eventually want to do this, but it's not planned. Yeah.
In general, OpenStack doesn't rebalance things anyway.
Yeah.
Right?
So that's since the abstraction there is right. Overcommit is how you balance things out. You allow yourselves to overcommit. Then if there's idle things, you don't lose. That's the approach. So yeah, it's not planned.
Okay.
Can you live migrate a VM when all these extra specs?
That's a very good question.
So I'll repeat it, sorry.
Okay.
Once you have defined a VM in Kilo, let's say with all these extra specs and whatnot, can you live VM migrate that VM and expect the same flavor and extra specs to be honored?
So that's a really good question, and the answer is no.
Okay.
But it's a bug. It's a bug because it's a bug in the Nova live migration code that we know about and we are fixing. I have some patches up to fix this, but they're a little bit rough. So I would not expect this to get fixed in Liberty. In current release,
it won't be in Liberty also.
It may not get fixed, yeah, because it's not. It's a pretty deep change. So
okay, thank you.
Okay, thank you very much for listening.